You're watching a Channel 98 NBISD TV production.
Hey out there in TV land, how y'all doing? Welcome to That Geometry Show. I'm your righteous host, Kevin Corpy, that's right. And today we're going to be doing lesson number 8. Love that number 8. It's all about triangles. If you wanted to know something about triangles, you've tuned into the right show, and I hope you stick around. Why don't you log on to that fabulous thing they call the internet, to www.newbraunfels.txed.net and download those documents. I'm going to be using them today. Grab one of those little writing utensil things they call a pencil and stick around and maybe you'll learn something. Let's get right to it. All right, lesson 8. This is going to correspond with your Glencoe Geometry chapter 4.1 and 4.2, all about triangles. Now by the end of this groovy lesson, you should be able to, number 1, identify the different parts of a triangle, classify triangles by their angle measures, classify triangles by their side lengths, and oh yeah, find the measure of different types of angles inside of a triangle. Okay, now we encounter triangles every day, right? In all shapes and in all sizes. And as you all know out there, all triangles have 3 sides and they have 3 angles. Look at this little pumpkin guy over here. Jack-o'-lanterns, they got triangles for eyes. See that? 3 sides, 3 angles. And look, he's smiling because he's on a geometry show. Now, we can classify angles or triangles 2 different ways. One way is we can classify them by the measure of the lengths of their sides. And that's what we're going to do first. So the first one we have is something called an equilateral triangle. In an equilateral triangle, all 3 sides are the exact same length. And we usually denote that by putting a line, dash, whatever, on each of the 3 sides. That shows that all 3 of those side lengths are the same length. They're congruent sides. Now, an equilateral triangle is always equiangular, which we're going to talk about here in just a little bit. The next type is something called an isosceles triangle, and that one's fun to spell. An isosceles triangle is a triangle, of course, that has at least 2 sides the exact same length. In this triangle here, that looks to be this side here and that side there. So we'd put 2 dashes. Now an isosceles triangle may be a right angle, may be an obtuse angle triangle, or it may be an acute triangle. And we'll talk about what those are here in just a little bit. But the important thing to know about an isosceles triangle is at least 2 sides are the same length. All right. So now we've got something called a scalene triangle. And in a scalene triangle, of course, it's a triangle like this one here. None, I repeat, none of the sides are the same length. They're all different. Now, a scalene triangle, it may be a right triangle, an obtuse triangle, or an acute triangle. So in this triangle here, I can't put marks on any one of the 3 sides because they're all different. Therefore, it's a scalene. All right. Yeah, so that's one way, classifying triangles by their side length. Another way we can classify the triangles is by the measure of their interior angles, the angles on the inside of the triangle. Okay, so the first one is called an acute triangle. And in an acute triangle, all the angles, not some of them, but all of them, are less than right angles. That means they're all less than 90 degrees, like in this one here. Now, in an acute triangle, it may be an equilateral. All the sides could be equal. It may be an isosceles, which would have at least 2 sides equal, or it could be scalene. All 3 are different lengths. All we know is that all 3 angles are less than 90 degrees. Got it? All right. In an obtuse triangle, that's the next kind here, we've got one angle that's greater than a right angle, which means it's bigger than 90 degrees. And if you look at this triangle here, that would appear to be this angle here. It's a little bit bigger than 90 degrees, which would be a right angle, and so we'd call that an obtuse triangle. Kind of fun to say. Say obtuse triangle. All right, look at those mean-looking bats there. Now, the next kind of triangle is called a right triangle. Now, in a right triangle, one of the angles is actually a right angle. That means it is 90 degrees. And remember, in a right angle, we denote 90 degrees by using this little mark here. It's a little bitty box in the corner. That means that angle is the right angle, and it's 90 degrees exactly on the mark. No more, no less. Now, a right triangle, it may be isosceles. It may have at least two sides that are of equal length, or it may be scalene. It can all be different. Notice that I did not say that a right triangle can be an equilateral. That isn't going to work, and we'll come across that again later in the lesson. Now, the last type of triangle classified by angle measure is a special dude that we've already mentioned today called an equiangular triangle. Now, in an equiangular triangle, all the angles are congruent. That means they have the exact same measure. And what is that measure? Did I hear you ask? Well, it's got to be 60 degrees, okay? And I'll show you why later on. Right now, just take me on faith that every angle is 60 degrees. Now, an equiangular triangle, if they're all 60 degrees, can we further classify it? Well, 60 degrees is less than 90. So all the angles are less than 90, which means it's also got to be a special type of acute triangle. And guess what else? It's always going to be equilateral as well. So we know that all three sides are the exact same measure, okay? Now, here's the cool part. Every single equilateral triangle is also an isosceles triangle. You know why? Because remember, isosceles said at least two sides had to be the same length. If all three of them are, that fits the definition. So every equilateral triangle is also isosceles, but not vice versa. Hey, what was that? Monster in the house. All right, let's take a look at some examples. Number one, which does not describe triangle PQR. That's this triangle right here. Well, let's see. We got four answer choices. Which one does not? Is that triangle acute? Well, let's see. We've got a triangle. We've got three sides marked up there. That means that all three sides must be equal. That means that this dude has to be an equilateral triangle, right? Oh, well, look, that's choice C, so we know C is good. It's good to go right there. Now, what else do we know? In an equilateral triangle, remember, all the angles are 60 degrees. So if they're all 60, they're all less than 90. That means it's got to be an acute triangle as well. So, oh yeah, 8 is a good choice. It does describe it. Now, coming over here, let's see. Isosceles or obtuse? Well, there's no way that this can be an obtuse triangle because there's not a single angle bigger than 90. They're all less than 90. So that does not describe our righteous triangle right here. Now, is it isosceles? Well, that's what I just talked about when I excited the monster. An isosceles triangle, yes it is, because it's equilateral, remember? And every equilateral triangle is also an isosceles triangle. All right, cool example. Let's do another one here. Number 2. In triangle ABC, it is a what? Well, let's look at choice A. Isosceles and scalene. Is that true? Well, isosceles means at least two sides are the same length. Let's look. I've got a side length of 7, 5, and 6. None of those are the same. So there's no way, no how it's going to be isosceles. Besides, can anything be isosceles and scalene? That's a contradiction of definitions, man. That's never going to happen. All right. Or is it an equilateral triangle? Are all three sides the same lengths? Well, only when 6 equals 5, which equals 7. And man, even at Halloween when 5 and 7 are going dressed as number 6, that doesn't make them equal, man. So they're all different. So there's no way it's equilateral. Is it scalene? 5, 6, 7, all different. So yes, it is scalene. But don't jump and just pick answer C because there's another thing attached to it. But not acute. Oh man, this is acute triangle. Let's see if it also is an acute triangle. 50 is less than 90, 75 is less than 90, and 55 is less than 90. So it is acute, and this choice is saying that it's not. So I don't really like that choice. That means the last one by default is correct, I hope. Scalene, 5, 6, 7? Yeah. And acute? Oh, yeah. It's all less than 90 degrees on the angles, and each side is different. So we know that it is scalene and acute. Now, speaking of acute, I got a cute skeleton right here who's going to introduce the next problem for us. Here he has a little triangle here, triangle EFG. And he wants to know what type of triangle he's showing us there. Well, let's see. Is it a right isosceles triangle? Well, we know it's a right triangle because it's got that little mark right there. So I can really get rid of choices B and choice C. There's no way it's going to be acute because that says all angles have to be strictly less than 90. And that ain't going to happen if one of them is 90. So it's got to be either A or D. It comes down to saying, is it isosceles or is it equilateral? Are two sides congruent or are all three sides the same measure? Well, I've got marks on these two here, and I don't have a mark on this side, so I can't assume that it's the same length. So the best I can do is hope for it being a right isosceles. Now, remember what I said about right triangles? It's never going to be an equilateral triangle if it's a right triangle, because that means that the other side length would have to be the same as the other. And if I just try to draw something that's roughly the same length as the other two, I'm going to stop right there. And notice it's too short to even make the rest of the distance. So never will a right triangle be an equilateral triangle. All right. We're going to go ahead and take just a little bitty break here for some valuable public service announcements. But I hope you don't go anywhere because they're going to be right back to do that righteous thing we call geometry. Don't go away now.
He's fearless, focused, and 100% hypoallergenic. Send someone's teddy bear to Congress on November 7th. This message paid for by Citizens for Someone's Teddy Bear.
If you're not voting, then who are you electing?
So you used to be taller. What happened?
What happened? Pressure. The pressure to be so cool and so popular and to never say the wrong thing to anyone so I'm cool with everyone. The pressure to drink and get high. Pressure happened.
So now what?
I don't know, but this isn't working.
Hey out there, welcome back. Did you miss me? Come on, you don't have to lie. I know you did. We're going to get right back to that geometry show. Let's do it. Okay, now we're going to look specifically at isosceles triangles here. And I know you've thought we've classified enough about triangles, but now we're going to talk about the special parts of an isosceles triangle. And this diagram here will help us see what we're talking about. All right, we have something called the vertex angle. Now, a vertex angle is, of course, an angle, but it's the angle that is what we're going to say is opposite the base in an isosceles triangle. That's going to be this one up here. Now, in an isosceles triangle, remember that two sides are congruent. So the vertex angle is the angle that's formed by the intersection, or basically where the two congruent sides meet. That's the vertex angle, okay? And it's opposite the base, which brings us to our next fantastic definition, the base. The base is going to be the side of the isosceles triangle that is on the opposite side of the vertex angle. Draw that little line, boom, right there you hit the base. Now, you don't want to just make the assumption that the base is always on the bottom, because look what I can do with this piece of paper. I can turn it sideways, see that? Now the base is still here because this is my vertex angle, because these are still my two congruent sides. But now the base is on the side. So you can't just call the base the bottom, although that would be convenient. The base is always opposite the vertex angle, so you got to clearly identify it first, man, okay? Now, the legs. We actually have two legs in an isosceles triangle, and the legs are going to be either one of the two congruent sides, the two sides that are exactly the same length. We're going to call those the legs, and those are the ones that meet to form the vertex angle. Then we've got two other angles, and we're going to call them the base angles. And the base angles are going to be the two congruent angles. That means they're also the same measure. So I'm going to put double marks here since I've already put a single mark for the vertex angle. That means that those two are the same sides, and they're opposite each of the two legs. So opposite this leg is that angle, opposite this side is that angle. And notice that the base angles actually touch the base side. All right, so digest all that right now because we're going to go ahead and put that to use. It's a lot of information. Let's look at an example. We've got little witch here bringing us this problem. She's pretty proud of this problem. She cooked it up last night in her big black cauldron. Triangle RST is an isosceles triangle with angle S as the vertex angle. Hey, it's nice when they tell us what the vertex angle is. It's this one here. Now, it says if the measure of ST is 3x minus 11 and the measure of segment SR is x plus 3, and if the measure of segment RT is x minus 2, we're trying to find the actual measurement or the measure of segment RT. Well, that's not going to be a problem. Segment RT in this problem would be the base, even though it's not on the bottom because it's opposite our vertex angle. Now, how are we going to set this up? We're not afraid of a few x's in a little algebra. We know that these two legs are congruent, so we can set their algebraic expressions equal to each other. So 3x minus 11 has to equal x plus 3. And then a little razzle-dazzle with the algebra, collecting the x's on the left. 3x minus 1x gives us a 2x. Adding 11 both sides, voila, we get 14. And a little magic spell, which is nothing really more than dividing both sides by 2, alakadabra, gives us 14 divided by 2, which is 7. Now, you box the answer, you feel proud, but that's not the final answer. Just because we solve for x doesn't mean we've answered the question, so be careful. We're trying to find the measurement of segment SR. Well, SR measurement is x plus 3. And what is x? It's 7. So let's add it together. 7 plus 3 gives us 10. So the base of this isosceles triangle, segment RT, is a measurement of 10. Now, let's do one thing here. Let's go ahead and verify that the two legs are actually the same length. We found what x is. It's 7. So we know that segment ST has a measure of 3 times x minus 11. Well, that's going to be 3 times 7 minus 11, which is 21, minus 11, which is, abracadabra, the number 10. Now, let's go ahead and look at what segment SR is going to be. Segment SR is going to be, I did this wrong. Forgive me. SR, man, groovy things happen. We just go with them. SR, I already found. It's 7 plus 3. That's 10. Did I really answer the question up here? It's okay, man. Hippie mathematicians make mistakes too. SR is SR. We're trying to find RT. I just boxed the wrong thing. Well, let's not leave the problem until we answer. What is RT? I'm going to sneak it in up here. The measure of RT is x minus 2. So it's something minus 2. Ah, right. Now we know that x is 7. 7 minus 2 is 5. So the base RT is actually 5, and we just verified twice that the measure of segment SR is 10, and they're the same length. Now, check this out. You've seen a witch's hat before, right? Look at that. Did you know that a witch's hat is actually an isosceles triangle? This side is equal to that side right there. Pretty cool. Even witches are into math. How about that? All right. Well, let's see if we can get going here now. There's another important property about triangles, and that is that the sum of the measures of all the interior angles have to add up to 180 degrees. Now, if the sum is anything other than 180 degrees, we don't have a triangle at all. And that's a very important theorem called the angle sum theorem. The interior angles always add up to 180 degrees. All right, so we've got a problem that's being given today by Mr. Dracula. And Mr. Dracula's problem is a real simple application of the angle sum theorem. Here's what he's asking us. He's created this triangle, and it's kind of hard to see, but this angle is 18 degrees. This angle is 27 degrees, and he's telling us to solve for x. All right, so let's go ahead and do that. Those are the interior angles of the triangle, so we know if we add them up, 27 plus 18 degrees plus x degrees, well, that has to equal the grand total by the angle sum theorem of 180. Doing a little bit of arithmetic here, 27 plus 18 is going to be 45. Degrees plus x equals 180. Subtracting 45 from both sides, I get x is 180 minus 45, which is 135 degrees. So the answer is B. Okay, real easy application. Here's another one. Example. What is the measure of angle D, that's this right here, in triangle DEF? Well, man, that's a simple instruction. Let's look at the triangle. Notice that little mark right there. That means that it's a right triangle, which means that that angle is 90 degrees. So the sum of all the angles measures has to equal 180. So I know the measure of angle E, which is 3x plus 2, plus the measure of angle D has to be 2x plus 3. And I know if I add it to that 90 degrees there, then that's going to equal 180. Well, right triangles are pretty special. If I subtract 90 from both sides, I'm going to go ahead and combine this over here. 3x plus 2x is 5x. 2 plus 3 is 5. But look what I get when I subtract 90. 180 minus 90, that gives me 90 degrees. So if one of the angles is 90 degrees, then that means the other two have to be complementary. Remember what that means? That means that their sum also has to equal 90. That's a pretty cool property of right triangles. Now again, a little algebra solving. I subtract 5 from both sides. 90 minus 5 is going to be 85 degrees. And dividing both sides by the fabulous number 5, I get 17 degrees. Now again, you're going to feel real happy that you solved for x. But the question says, what is the measure of angle D? And I'm going to do this one right this time. The measure of angle D is 2x plus 3. And what did we just find x to be? It's 17 degrees. So now I'll plug it in. 2 times 17 is going to be 34 plus 3. And I get that it is equal to 37 degrees. All right. Now, can we figure out what the measure of angle E is? If they have to add up to 90, then we could say that the measure of angle E is going to be the complement of 37. So it's 90 minus 37, which is going to be 53. So if this angle is 53 degrees and this angle is 37 degrees and that's 90 degrees, then they all add up to 180. We're feeling pretty confident about that because we've checked our answers. All right. This example brought to you by the Black Cat. Which statement is not true? That means which statement is false. Okay, looking for the untrue or false statement. A triangle cannot be scalene and isosceles. Well, we know that it can't be scalene and isosceles at the same time. They're saying two different things. This says all sides different, at least two sides the same. So that is actually a true statement because it's saying that it can't be that. So yeah, that's true. Got to read these things carefully. Part B. In an isosceles triangle, where at least two sides are the same length, the base is congruent to one of the legs. Well, in general, remember, in an isosceles triangle, the two legs were congruent. The base is only going to be congruent to one of the two legs, or both of the legs, if it happens to also be equilateral. But in general, an isosceles triangle is not equilateral, so I'm thinking that this is a false statement, which is not true. So I'm going to circle it as my answer, but I'm also going to keep going and check the others, just to make sure I got the right choice here. Plus, it's also kind of fun. Choice C. A triangle cannot be obtuse, one angle bigger than 90 degrees, and contain a 90-degree angle. Well, that's not going to happen because one of them is bigger than 90 and one of them is 90. Then when you add those two together, you're going to exceed 180 degrees, which means you don't even have a triangle, man. So it's saying that that can't happen, which means that the statement is actually true. Okay? Choice D. A triangle can be obtuse, one angle bigger than 90, and isosceles. Oh yeah, let's draw an obtuse triangle. That angle's bigger than 90. Is it isosceles? Well, yeah, if those two sides are exactly the same. This might look like a roof truss. If you crawl up in the attic, get your parents' permission first, take a look up there. You might see a roof truss that's going to be an obtuse triangle that's also going to be isosceles. Okay, now it's time for my favorite part of the show called the Say What, Man? Okay, here we go. I've been talking a lot about interior angles of these triangles, and you've been like, well, interior, of course, that's what a triangle has. Well, would you believe it that triangles can also have exterior angles? Yeah, that's right. That's angles on the outside the triangle, okay? Outside. Now, let's look at this diagram here. In this diagram, we have triangle with angles A, B, and Y. I know it's not the alphabet, but it works. A, B, and Y. Now, if I extend the bottom line of this triangle out, I can create another angle that's formed by one of the sides of this triangle. That's called an exterior angle. Okay? And there's more than one exterior angle per triangle, but we're going to look at this one here. Now, there's an important property about exterior angles. The exterior angle of any triangle is equal to the sum of the interior angles at the other two vertices. That would be angle B and angle A. So x equals A plus B. That's what we're saying. This exterior angle is equal to the sum of those two. Okay? And if you're kind of wondering why that is, let's look at it and explain why. X and Y, those two angles, form a linear pair. So remember, they're supplementary. They add up to 180 degrees. Where else have we heard 180 degrees in today's lesson? Well, that's the angle sum theorem that says that the sum of all the interior angles has to equal 180. So if X plus Y have to equal 180, okay, and we'll say the measure of them, and if the measure of angle A plus the measure of angle B plus the measure of angle Y also have to equal 180, then what do we know about X and A plus B? Well, they are actually the same. They are equal to each other. Okay? So the sum of A and B is supplementary to the measure of angle Y. That's pretty cool. That excited the monster again. Hey, there's the monster. Frankenstein's monster is going to give us the last example here today. Okay, it says in this triangle, what is the measure of angle B if the measure of angle A is x plus 3 and the measure of angle B is 3x plus 1? Well, we don't know what that measure is right there. But look, we do have an exterior angle right there. It's 112. So we know then that 112 is going to be equal to the sum of the two interior angles on the other side called remote interior angles. So I can say 112 is equal to 3x plus 1 plus x plus 3. And now combining like terms, 112 equals 4x plus 4. So 4x has to equal 112 minus 4, which is 108. And finally, dividing both sides by 4, I get this remarkable number called 27, a very groovy number. And so that would be x. Now we have to answer the question. The measure of angle B is going to be 3 times x plus 1, which is 3 times 27. 3 times 27 is 81 plus 1. So we get that its measure is 82 degrees. Don't forget to answer the question every time. Hey, man, that's it for today. I know you want more, but we're running out of time. So I hope you had a groovy time like I did. You know what? If you ever want to pick my brain, you can email me at kcorpy@newbraunfels.txed.net, and I'll get back with you as quickly as I can. And until next time, I'm your groovy host, and I will catch you on the flip side. Oh, yeah.
You're watching a Channel 98 NBISD TV production.